Okay, good afternoon, everybody. I want to thank you all for joining us on our last webinar of 2012. Today we're going to be talking about analyzing electrical sound files, and we're very happy to have Joe Gierlach with us from TEG Corporation. He's got some really great sound files he's going to be playing for us and walking us through how to really understand what it is we're listening to, what it is we're seeing on our spectral analysis. So it should be a really good kind of a different webinar than we're used to, but I think everybody's going to really benefit from listening and seeing what he's going to be showing and playing for us. But I will, just a housekeeping, since a lot of what he is going to be doing is playing sounds for us, just be sure that if the sounds aren't coming through real great on your speakers, I know this sounds silly, but we had this issue earlier when we were doing a little dry run. Just really make sure you turn your volume up, even as loud as it can go. The talking part, you might need to kind of turn your volume down a little bit, but when those sounds are playing, to really hear them, some of you might need to kind of crank your volume up to be sure you're getting some good sound coming through. Again, seems trivial and elementary, but I'm sure that some of us, like myself, need that reminder every once in a while. So hopefully that'll work for everybody. So just real quick, I've got a couple intro slides here. So again, UE Systems, we've been providing ultrasound technology for over 40 years now, or close to 40 years rather, helping folks with their condition-based monitoring programs and predictive maintenance programs. And what really started out more as a tool that folks use for leak detection has really evolved over the years with numerous applications, including electrical analysis. So more and more we're finding folks are really digging in and utilizing our technology and products for electrical analysis. So this webinar seemed timely as we were getting a lot of folks asking for more information about how they can really integrate this technology into their programs to use this for electrical analysis. So we're really happy to have Joe here to walk us through some of that. On your screen now you'll see our interactive information kit. I know we show this every webinar, but we do usually have folks asking to have us send this to them. So if anybody would like this, it's just a really great kind of little mouse click to read more about our different products, the softwares that we have, different seminars that we've got, the webinars. Is just kind of a at-a-glance tool, so we're happy to email this to anybody, and if you'd like it, just shoot me a note in the questions box and I'll be sure to note your email address and we'll get this right off to you. And that brings up another housekeeping. We do love to get questions from you all, and we'll stop Joe in the middle of the presentation even to get some questions answered, so feel free to type in a question as it comes up. You don't have to feel the need to hold those till the end. We'd love to kind of try and make this as interactive as we can, knowing that it's really, we've got folks throughout the world right now listening in. So please definitely ask those questions. We'll get questions answered that we can during the webinar, and those that we're just not able to get to due to time, we'll be sure to get those answered and emailed to you after the fact. So without further ado, I'm going to pop the screen over to Joe and we will get started. So give me 1 second here. And Joe, I am making you the presenter.
Okay.
So I will welcome you and I will turn myself off.
Well, good afternoon, everybody, and thank you for joining us today on the webinar. As Maureen said, my name is Joe Gierlach, and I am in charge of the Technical Training and Support Department at TEG Service in Pittsburgh. I've been involved with the ultrasound for a number of years now and had the very good fortune of being involved with a lot of people throughout our network who are utilizing the ultrasonic technology in the electrical applications. And it's a very common theme that a lot of our guys have difficulties using this effectively as it relates to the spectralizer. And that does seem to be the trick, and I do not want to oversimplify what we're going to talk about today, but if you break down and characterize the type of faults that we're looking for in electrical systems, there's really 5 or 6 that are present, and you're familiar with the majority of them being arcing, tracking, corona, mechanical looseness, vibration, and contact chatter. And I have a number of different recordings from our field today I'd like to share with you, and just kind of overview how I use the spectralizer in the real world, and the way we try and teach our guys to be able to effectively determine what type of fault they're looking at. And for purposes of today, I'm going to focus purely on the FFT analyzer and the time series domain. And setting that up for electrical depends on a number of factors in both of them, and I will try and explain that as we go along. I want to talk about some of the different faults, what I call the spectral footprints, things that I look for in these recordings, and each one of the tools serves a specific purpose when it comes to any of these faults. And what I preach to our guys is you have to use both tools. There's no way to be able to definitively tell what a fault is if you are only using one tool. So we'll begin here. When Spectralizer opens up, we all know what it looks like. And in most cases, if it's the default settings, it's not going to be configured in a fashion we want to use it for electrical wave files. And on the FFT, the decibel scale on the left-hand side here is going to be relative to the recording itself. In other words, it will need adjusted specific to each recording, and what I try and do is to fill my screen up with the areas of interest to give me the best view of the frequency spectrum. On the bottom axis here, where the frequency is displayed from the heterodyne signal, I set this up by double-clicking the last number in the graph, and anywhere between 8 and 900, and I'll set this to 900 for right now, is adequate and has the most useful data that we utilize for the electrical applications. So for the purposes of that, we will set this up at 900. The next thing is your harmonic markers. And this can be done before or after a wave file is played, so we'll mess around with these settings as we go along so I can show you the views. The harmonic marker varies depending on what part of the world you're in. For North America, obviously, us in North America will operate on 60 hertz systems. Elsewhere in the world, we'll be interested in 50 hertz harmonic cursors. The other thing I will call attention to is at the top of the spectralizer, we have the number of samples in the FFT. And by default, the spectralizer is set up to launch at 4096. And in a lot of cases, for my purposes, I choose 8192 to get more samples for the recording that I am playing and allow for better resolution on the data that I am looking for. So we'll go ahead and start with the FFT and a wave file from a customer of mine in Maryland. And in this particular recording, it was on a 34 kV switch, and there are 2 different recordings here. An initial recording that the technicians made on a first-year visit, and a subsequent recording that was done approximately 6 months later. One thing I stress to our guys is what we hear in the ultrasound should be an indicator, but it's never a definitive, concrete assessment of what's going on. For those of you who use infrared cameras, for example, there are a lot of things that look a certain way that are really not that way. And the same thing applies to ultrasound. To put a picture on the sound is to be definitive. And with each of these faults that we're talking about, there is a signature and a pattern in both the FFT and the time domain that we can determine very accurately. So I will play this first recording here that was sent to me approximately a year and a half ago. Be sure your speakers are up. Now I'm going to pause that recording there. As you can see, it's approximately a 40-second recording. And we encourage our guys to get at least 20 to 30 seconds of good data. So we have a good recording. We can determine if there's any changes going on throughout the recording period. Now, at first glance on the FFT, this does not look very useful. However, the tonal quality, if you listen to the recording, we could hear some pops within the recording over some both ambient noise and electrical components. So when I first set up a WAV file, I want to fill the spectralizer screen up here with as much of the recording data as necessary. So on the frequency spectrum, I'll find the highest area here, and this is going to be approximately a -52 on the dB scale. So I'm going to double-click the top number, type in -52, and hit the Enter button. And as you can see, it fills more of the screen up, and I'm just going to drag it with the hand tool and pull it down just a little bit. So now I can see some activity in here, and I'm going to go ahead and turn on the Harmonic Cursor. I'm going to type in 60 Hertz, since this was in North America, and turn the cursor on. And I'm going to continue the recording here for just a second, and what I am looking for is what I characterize as fault frequency peaks on the 60 Hertz harmonic. One key characteristic with electrical recordings is relative to faults, we will see certain 60 Hertz spikes or peaks in the frequency spectrum. The number of spikes or peaks that we observe depends upon the type of fault and what's happening relative to the electrical sine wave. So I'll play this some more, and let's observe what happens to these peaks. So what does that tell us? Well, if we look across the spectrum here, I'll pull this down so we can see. Here's our first 60 Hertz harmonic on the left-hand side, and we can determine that as well looking on the bottom axis here in between 48 and 75, and then your subsequent harmonic frequencies here of 120, 180, 240, 300, and so on up the line. I'm looking for these peaks that occur right on certain 60 Hertz harmonics. So right here at 120 Hertz, we can see that we have a small peak that's hitting right on the 120 Hertz harmonic. There's a shift here at 180. It doesn't really hit on that. Nothing at 240. And right here at 300, you can see it beginning to peak and hit right on that frequency. And then further out on the spectrum, nothing really hits directly on the harmonic. So the way I would characterize this is we have a fault frequency in the very beginning part of the spectrum on 260 Hertz harmonics. The other thing I look at on FFT is the amount of frequency noise that is in between each of the harmonics. So if we look in between each red screen, we can see there's an abundance of activity or frequency noise that's occurring in between all 60 Hertz harmonics. Those two things right there are a signature that I am looking for that tells me one and only thing. Either the recording is related to an electrical anomaly or it's related to a mechanical or some other type of anomaly. With the electrical type faults, and specifically we'll refer to tracking and arcing, we will see a couple of 60 hertz fault frequencies, and then they will drop off of the spectrum as we move out further to the right here toward the 900 setting that I have on this particular display. The frequency noise that's occurring within there is related to where the discharges of energy, depending on if it's tracking or arcing, are taking place and occurring relative to the electrical sine wave on a 16 millisecond time base. In other words, one electrical cycle is a time base of 16 milliseconds. A discharge of energy can occur at any point or multiple points within that 16 milliseconds, and that is one of the contributing factors to this activity that we see in between each 60 hertz harmonic. So with the frequency analyzer, at least with arcing and tracking and some of the mechanical faults that I'll get into a little bit later, they tell me it's electrical in nature or it's not electrical in nature. But it does not tell me what type of electrical fault that I may have. Now the next thing I'll do here is I'm going to set this particular recording as an overlay. And what I mean by an overlay is I will play another recording on top of this to compare the signatures. And first I'll turn the overlay on down here at the bottom where it says FFT overlay control, and I'm going to hit set. And what that'll do is it'll keep this frequency spectrum for that recording as I go in here to open up another recording. In this particular case, I'm just going to compare the two visits. And in the world of ultrasound, comparisons are just as critical as anything else. And I'm looking for two things here. Number one, do I have similarities that would suggest they are both electrical in nature? And number two, I'm going to try and make the determination, has there been any deterioration over time? In other words, has the severity become worse with this particular fault? And severity is a tricky but important thing to determine, because in a lot of the mechanical applications using ultrasound, we rely upon decibel level to help us gauge severity. And the thing I can't stress enough to our customers and to anybody using the ultraprobe in electrical applications, the decibel level has absolutely nothing to do with the severity of the fault we are talking about. The decibel level tells us one thing and one thing only. How close are we to the source of our emission as we are making our recording? The severity is gauged by the frequency analysis and the content in the time domain. And I'll get into that a little bit further, but right now let's see if we have similarities in these two recordings. As I open the new WAV file, you'll notice the overlay turns red, and I will run the next WAV file on top of that. Okay, and I'm going to stop it there for right now. Now, obviously, this display is not very useful to us because there's been a shift in the decibel level, as you see. That is ultimately going to mean a shift in the severity, but not based upon the decibel level. So now I have to readjust my frequency graph again so that I can see both recordings in the display. And all I'm going to do is use the hand tool over here on the right, and I'm going to drag the display down to see where my highest peaks are. And in this case, we're going to call it about minus 39. So I'll pull this back up. I'm going to double click on the top number, type in minus 39, and hit enter. And now we can see that we have both recordings in the view here. And this is a little bit different than the first recording in that we don't have this peak on 120 like we did before. However, there's one out here at 240 hertz. And as we come further out the line, the shifts are off of the harmonic and nothing's really hitting right on it. However, the other similarity that I see here that I would focus in on is the activity or frequency noise in between each of the harmonics. One thing I'll call attention to as well was the tonal quality of that recording. If you listen carefully, you could hear pops within that recording, and they were far more pronounced in this recording than the previous recording. So the tonal quality means something as well. And using the FFT here, what I would determine looking at these two spectrums is there's enough similarities looking at the frequency peaks and the noise content in between each harmonic to say they are similar in nature and most likely electrical based on the frequency noise. It still doesn't tell me the type of fault. So for this, what I'm suspecting there is an arcing and or a tracking event. It's a very common fault, and you can hear these things going on as well as visualize them. Another thing that happens on these higher voltages, we all know about corona, and the two different types of corona being nuisance or normal corona, and then we have destructive corona. The major difference between those two is that one is naturally occurring due to the stresses on the voltage levels. The other one takes place when there are breakdowns in insulating systems and you begin to get discharges of energy along insulators or conductors. When that takes place, it begins to affect the timing of where the discharges are and mask that on top of the known predictable stresses associated with corona. With a normal nuisance corona event, the highest stress on the electrical sine wave is on the negative half cycle, and that occurs on a very predictable, repeatable, known time base of every 16 milliseconds. So that being very consistent, uniform, and repeatable on the frequency analyzer at least, you get a nice display of uniform, consistent 60 Hz harmonic peaks. As the discharges of energy begin to occur on top of that, we will lose or we'll see a reduction in the 60 Hz peaks on the outer part of the spectrum. And that's because on top of the stress on the negative half cycle, at other points on the electrical sine wave, you have these discharges occurring. That impacts the timing, and it changes the frequency spectrum in the form of masking the outer 60 Hz harmonic peaks. But in this case, I don't see enough 60 Hz peaks to even say there's corona present. But I do suspect that there's going to be an arcing and or tracking event. To determine that, I need to switch to the time series analyzer here. And as we see on this one, the signal on the second recording was overloaded. And that creates some problems as well, which I will caution everybody on. When you make these electrical recordings, it is critical not to overload the signal in the spectralizer. What happens is you get chopping on the top and bottom of the analyzer, what's commonly known as square waving. And when you chop that data off, you cannot determine fluctuations or variations in the amplitude that I'm about to talk about. So I will play the first recording in the time analyzer. And again, I will stop it there. Now, a couple of things you can do in the time analyzer here, and you notice that that's not an overloaded signal. We do not have chopping on the top or bottom of this display. At face value, one may not know what to look for here, but I would encourage everybody on the time analyzer. We have the x-axis here going left to right on the screen of time, and then we're going to think of the vertical axis here as amplitude. The time is self-explanatory. It looks at a specific time in the point of a recording. And within electrical components, there are certain components that should have no ultrasonic emissions. There are other components that have known or normal emissions. And in both cases, when you have other components taking place, you have to be able to pick those out and visualize them. The time analyzer does this the best, in my opinion. So what I'm looking for here, if I were to characterize what a tracking event looks like, in other words, making it a visual image using the time analyzer, the easiest way to say would be we are characteristically going to have this band of white noise across the time analyzer. That's partially the instrument plus what we may be recording. These spikes that we see deviating from that center baseline are going to be representative of discharges of electrical energy, which is what you would have in both an arcing and a tracking event. And I want to look at certain points in both time as well as the overall recording. So by double-clicking with your left mouse button the stop, you can get the entire 40-second recording in this case in the view of the analyzer. And just on the surface here, if you look across left to right, you will see that there is consistent deviations from that broadband white noise. In other words, we have these spikes going up and down consistently all the way through the recording. And the other thing that's noteworthy on these discharges is they are not uniform or linear in amplitude. And that's an important thing. What that tells us, the nonlinearity, says the intensity of the discharge is varying. So it's changing throughout the recording. It is not the same, and that's important to understand. The deeper or larger that the discharges get, the higher the intensity here. So we know we can look at this and see that there are discharges and they're not uniform in amplitude. That's one pattern or characteristic of a tracking event. And keep in mind, tracking is when you have these discharges along insulators. These events do not draw current, so it would not be detectable with an infrared camera. But it does damage the insulation, and it starts a path to ground, which subsequently can lead to an electrical arc over or flash over event. So that's the first thing here I'm looking for in the time analyzer, is these spikes or deviations from the center line that vary or change in amplitude. The second thing I need to look for is the other characteristic of a tracking event, and that has to do with how often is it taking place. In other words, if I were to break it down to one electrical cycle, within that 16 millisecond period, how many times does energy discharge on that sine wave? So I like to use a technique that I must credit Mr. Mark Goodman with, that he kind of encouraged me to use and taught me to use, called slice and dice. Instead of looking at the entire 40-second recording, I want to look at a portion of it. And this varies as far as how much you look at, what time period you look at, is going to vary depending on the type of anomaly that you have and how severe it is. So in this particular case, I'm going to choose this magnifying tool here on the right-hand side of the screen and pick a point in the recording here, about 20 seconds. I will click and hold the mouse and drag this across the recording for about a 5-second view. And when I release that, we can see at the bottom axis, we're looking from 18.5 seconds out to 24 seconds. So now, what can we see here? Well, we still see the broad band of white noise across the middle, which is to be expected, but now we can see with greater detail these deviations which represent the energy discharges. And we knew they varied as far as their amplitude, which tells us the intensity of the discharge, as I mentioned before, is changing or varying. So some discharges are higher intensity here than others down here. But I'm looking at times, specific times here. And as I look at some of the peaks, the question I ask myself is, are they uniform or occurring at exactly the same time throughout the recording or the cycle? And in this case, you can see some are spread further apart, some are more compact together here. So I'm going to zoom this in a little bit more, and in this case, I'm going to take it down to about 1.5 seconds right here. And now we get an even closer view, looking at our broadband white noise here, and I'm going to focus in particular on these several peaks right in here. And what I'm interested in is, will the timing between these big discharges be similar? It's a little hard to tell right here, but you can see there's differences. There's, on this very first one, we can see there's several discharges tied together, and then we have one large one here with a couple smaller ones. So I'm going to zoom in on these two or three right here and take the time base down even further. That's a little bit too far. Let me go back on that. Try that again. There we go. And I'm going to adjust my scale back. And I just like to have this filling up the screen because it's a lot easier for my eyes to see it, to be honest with you. So that illustrates it pretty good right here. We can see differences in the amplitude very well, and definitely differences in the spacing of the events. And that's the key thing on tracking. There's no predictable pattern on when this is going to occur, and this gives us a really good view of that. Right now I'm looking only at about 1/2 second of the recording. Now I had it. Sorry about that. Go back to here. And readjust this because I have happy fingers. Okay, and one more time here. Go back in here. There's a real good view of it right there. So now I'm looking approximately 1/2 second, as I said, and what we can see especially right here between 14.8 and 15.4 seconds, we have these amplitude, or the amplitude of these vary across time, but yet if you look at the spacing in between them, that is the key right there. And when you see these differences in spacing, that tells you that the timing of the discharges is not linear across the sine wave. Within that 16 milliseconds, there's no predictable pattern on when those discharges are going to occur. That's a key signature of tracking. With other types of events, such as corona, you would see, even on Nuisance corona, this is a predictable pattern where the ionization of the air takes place. The timing in between each one of these spikes on the time domain would be linear and uniform. That is absolutely not what we have, particularly right here, just to pick a slice. And I'll zoom in on that just a little bit more using the magnifying tool, and we should be able to see that a little better here. There we go. That provides a real good view. So between this discharge and this discharge, we see the distance in between there is strikingly different between these two and these two, and these two. That is a signature of a tracking event taking place on an insulator. So summarizing that for this particular event, when I see on the frequency analyzer going back to this, I'm looking for certain 60 hertz peaks. There's no good way to say how many, but a 60 hertz system will have some peaks with an abundance of frequency noise in between each of the harmonics throughout the spectrum. That tells me it is electrical in nature. When I come to the time analyzer, I'm looking for both variations in the amplitude as well as differences in the timing where the amplitude deviations take place away from the white noise. So that's one type of event there. The other thing it indicated to us was the degradation over time. I'm going to bring up the second recording of that same 34 kV switch. And
hey, Joe.
run.
Oh.
Yes.
I'll wait till that's done.
Yes.
I'll wait till the sound's done.
Go ahead.
Sorry. I just had someone that real quick wanted to get a little just kind of basic explanation of electrical tracking, since we don't necessarily have all folks on here that are super in tune with the electrical side of things. So if you could just go over that, that'd be great.
Sure. Just for the benefit of those that may not understand the term tracking, the easiest way to think of this fault in an electrical system, it's referred to or known as baby arcing. And tracking occurs when there is a breakdown in the properties of the insulator and it's unable to contain the stress of the voltage. So the insulation or the insulating system weakens, and it allows the voltage potential to escape its system, and it will discharge along that insulator. It's sort of like a spark, if you want to think about it like that. So this is a continuous type of event as we get insulation breakdown, foreign contaminants, or moisture on insulators that allows the discharge or movement of this energy. So does that answer the question adequately?
Yes, I think that helps.
Okay. So going back to this second recording, two things I want to call to attention here is on the bottom of the display, the very bottom center here, I want everyone to watch what happens when I play this file again. And I'll stop it right there. We saw the word overload, and I just want to take a second and stress this point, especially in electrical applications. That's the last thing that you want to see on the time analyzer. The problem with that is it cuts the data off on the top and bottom of the display, and that takes away things that we need to analyze. So I'm going to change this setting here so I can see the tops and try and demonstrate where that would square wave to a degree. So I'll stop it right there. Unlike the first recording, this will be able to show us and demonstrate visibly the degradation or deterioration in this event. The translation to that would be, it has gotten or become more severe since the last recording. Not just in the tonal quality, but when we look at the time analyzer for the entire 35 seconds, we see this broad band of white noise here has become thicker, and we have more discharges more tightly compacted. This is hard to see on the full view, but as we zoom in, you'll see the discharges of energy are occurring more frequently. And that's the key thing as well, because we talk about severity. How bad is something? With a tracking event, my experience has shown the worse that a tracking event becomes, the more frequently the discharges of energy are taking place in the insulating system. And they become more compacted in here. And we can see an example of that to the left. There are many discharges right here in a very short period of time that are different, happening at different points in time. So the length of the discharges are longer periods, and they are more frequent throughout the recording. This is a key indicator that the fault is getting worse. If we gauge severity on a tracking event, we want to look at how often are the discharges occurring and how frequently they are occurring, because no two tracking events are exactly the same. They are very different in how severe they are. It depends upon the type of insulating system, the operating voltage, things of that nature. But it becomes worse when we see this increase in the number of discharges taking place and how frequently that is taking place over the time of the recording. A different type of tracking event here on a different voltage will demonstrate that. This next one is actually on a lower voltage system, and I believe it is in this paper. And this is on a 20 amp circuit breaker in a 208 volt system. So it's an internal tracking fault on a circuit breaker feeding a server. So I'll let this play first, and then we'll talk about it. So that was a 10-second recording. The recording was performed using the contact module with a frequency setting of 25 kilohertz on the instrument. And this frequency display is somewhat different than the last recording that we looked at. Again, I'm going to adjust this so we can fill the screen up and be able to see more of the data. That'll work right there. And what we can see on here is a different frequency spectrum. Again, with the 60 hertz cursor on, over here at 60 hertz, there is not a frequency spike or peak, but there is one here at 120 hertz, a small one at 180, another at 240, and that is shifted just slightly out here at 360 and nothing else out here. So again, a couple of 60 hertz peaks, although not big. It changes over time with the recording. We'll play this one more time. So the first signature of a tracking event using a contact measurement is verified in this spectrum. We have several 60 hertz peaks, and there is an abundance of frequency noise that's taking place throughout the recording. Now, another type of event related to vibration, that would be a mechanical issue. You would have a similar spectrum, but all the 60 hertz peaks would hit. I will play an example of that shortly to show you the difference in the frequency spectrums. But what will be absent on that type of issue is this frequency noise, or the activity that we see going on between here. Now, in the tonal quality of the recording, you could clearly hear a buzzing sound with, I will call it Rice Krispies, a lot of snap, crackle, pop on top of the buzz. Those are the discharges. Again, using the time analyzer, we can visualize that. And if we watch the entire recording, we're going to be able to see this change, amplitudes and timing. So I'll run this one more time. Now, the very end of that recording provides an excellent view of the intensity changes and the timing changes on that tracking event. Zooming in on this portion of the recording right toward the very end, we can see how the spacing in between these events, particularly between these two events, and these next 3 or 4. That spacing being different tells us those discharges are taking place at different points in time in a very wanton fashion. That is characteristic of a tracking event. It is not predictable like other events, and it can occur anywhere within that electrical sine wave. So this is an important consideration. It's the same type of fault, but with the different voltage system and the different type of measurement attachment, we still have the same signatures. Looking at the entire recording, there's our broad band of white noise. Here's our deviations from that center line indicating discharges of energy, and there are clearly differences in the spacing throughout the recording. That is your characteristic footprint of a tracking event. On a mechanical type of event, that would be slightly different, and I will pull up one here to demonstrate that. I believe it's this one. That's not the right one. This would be just a transformer vibration. Now, in that recording, some of us may be familiar with that sound, and it's normal for some transformer, in most transformers, to hum like that, if you want to call it humming. But look at our frequency spectrum. We have a very characteristic pattern here as it relates to transformer hum combined with vibration. And what we see normally, all the 60 hertz harmonics across the spectrum with this transformer hum are very pronounced. The difference is the amplitude. We can see every even number harmonic here has a lower amplitude than the odd number, the 60. Every 120 hertz has a lower amplitude from the other 120 hertz right here. That's characteristic of a transformer. In the time analyzer, we can see consistency. So it's a predictable event. On a 60 hertz system with the electromagnetic hum, if you want to characterize it as that, the timing is very consistent on a 16 millisecond time base, and that's illustrated by uniform spacing right here and pretty uniform amplitudes. What changes the height of these discharges has to do with load fluctuations. I've noticed that over time myself. We will see differences in the amplitude. That doesn't necessarily indicate a fault due to the linearities in the timing across this spectrum. How much time do we have, Maureen? I've lost track of time.
Sorry, I still had my thing on mute. Yeah, sorry, I was talking to nobody. We've got about 10 minutes if we want to leave a few minutes for questions, so maybe about 5 more minutes and then switch over.
Absolutely. I have a couple more here that demonstrate a couple other faults.
Great.
Okay, the next one here is early destructive corona. And I'll let this play first, and then we will talk about it. So this was off of an insulator, and it's on a 13 kV sub. I have to adjust this a little bit so we can fill our view up a little better. And right here. So we can see I have a 60 hertz harmonic here right in the beginning of the spectrum. I have a small 120 hertz harmonic. Then out through here, I don't get anything again till 300 hertz. There's another flat one at 360 and 420, and then pretty much nothing out here hitting on 60 hertz beyond 420. Now with corona, you're going to see all the 60 hertz harmonics at least out till 900 hertz on this frequency analyzer. Plus you will see the frequency noise here. So this spectrum, knowing the voltage, I know there will be corona present. So I expect 60 hertz peaks. I also expect, due to the ionization process, the abundance of frequency noise in here. That says it's electrical in nature, but it doesn't tell me the type of fault. When we refer to destructive corona, the easiest way to think of this, we still have corona occurring, but it becomes destructive when it begins to track. So when the discharges of energy occur, it's related to nitrates and nitric acid that forms, and when that forms, it degrades the insulators and weakens them. And again, we get tracking occurring on those insulators. So in the time domain, I'm really looking for the same tracking spectrum. Going back to here, if I rewind the recording and run it, so we can see that we have some uniformity in the timing. But we're also seeing some changes. If I look at the whole recording here, we see some variations in this amplitude. That's the same signature as tracking that would not be present in a purely nuisance corona event. As I zoom in, that becomes even more clear. We can see there are differences within the amplitude. That's part of the discharge intensity. And as we go in even further here, we can see there's changes in how long that's occurring. Not so much the spacing, because it's very early stages. But looking at the difference here between this next to the last one and the one previous, you can see how different it is in time relative to when the discharge is occurring. So this was very early stages, and this ringing as the discharges occur takes place for longer and shorter periods. The easy fix to this particular insulator was simply to clean it up, and this all went away. On a purely corona event, we'll just review that one time. I will play this on the FFT first. Now on that comes with everybody's spectralizer, and we're all familiar with it, but you can see two things here on the frequency analyzer. There's a tremendous amount of 60 hertz spikes or peaks through the entire recording. Nearly every 60 hertz harmonic has a peak, and we have a lot of frequency noise, a rich abundance here telling me, yes, it's electrical in nature. So that's common for a purely corona event that's non-destructive. We have all the 60 hertz peaks and a lot of frequency noise. That's in the FFT. In the time analyzer, what we see here is uniformity and consistency. That's a fairly uniform spectrum there, despite some deviations in the amplitude. So on pure corona, it's really easy to spot. You have the normal sound that we're accustomed to hearing, and we're looking for those two things on the frequency display with every 60 hertz harmonic and the abundance of frequency noise. One final one here comes off a 4160 volt motor starter. And in this case here, this was isolated down to a line side connection, and we'll just play the recording first. And as you can see, this gives a very strange looking FFT, but not to be alarmed. Remember, we're only looking for a couple of things here on the FFT as it relates to electrical faults. We're looking for, number one, do we have 60 hertz peaks or spikes? Number two, do we have an abundance of frequency, content, or noise? In looking at this one, there's one hit on 120 hertz here, very small, but no more until we get out here to 480 hertz and 530 right there. But notice the abundance of frequency contact. The tonal quality of the recording suggested popping noises. That's characteristic of them discharges as we hear it. But to visualize it, once again, we have to come to the time analyzer, and I'll let this play one more time. And even stopping the recording here, it really visualizes how the changes in amplitude or the intensity of the discharges are taking place throughout the recording. And looking at the entire 16 seconds, it shows the periods even better with the peaks and valleys. From the timing aspect, as we zoom in on this, that becomes even clearer how non-uniform that the discharges are occurring. There's no pattern to when in time we can expect the discharge. That is a signature footprint of a tracking event, and one thing we should be paying attention to whenever we suspect that we have that type of fault. And I always preach to our guys that you have to rely on these tools. You have to look for these signatures. To visualize a sound recording, you have to know what you're listening for to be able to pick out the tonal qualities, but then you must put a picture on a sound using these tools. So if you can become familiar with what the signatures are for the different electric faults, you can become very effective using the Spectralizer tool. And I know this is probably a little condensed, but them are some of the most basic techniques that we use in our organization as it applies to analyzing these WAV files. So, Maureen, I think that if you want to come back on, we can certainly field some questions.
That's great. Thank you. So, one of the questions that came in related to, you showed us a lot with the tracking. So, once you've determined the tracking is taking place, how much time before it truly becomes a serious issue or a failure occurs? Or is that even something that's a uniform answer? I'm not even sure.
Well, it's, I like to say, I have a tagline we use in our line of work, and I'll always say, I'm an electrician, not a magician. So I can't predict when something will fail. However, once a fault has been identified, it becomes even more imperative to increase the inspection frequency to see how fast it is degrading, as well as combining that whenever possible with a visual inspection to find out if the telltale signs of tracking are visible, which would be things like carbon trails and spider tracks and things like that, showing where the discharges were occurring.
Okay, great. Another question, is electrical discharge voltage dependent?
If the question's being asked in the context of do you need a certain potential or a certain voltage level to experience discharges, the answer would be no. Our experiences have shown down to 120 volts AC, we have identified accurately tracking events taking place.
Okay. Well, if they'll write in if that didn't answer that. And another question, can you set up a predictive timeline for scheduled replacement?
To be able to predict anything as far as replacement is difficult. My recommendation and the way we approach it, it all depends upon the severity of the event. In this case, yes, we focused a lot on tracking. The key thing to remember about tracking, it's destructive. It starts to degrade the insulators, and it is only a matter of time before it fails. Nobody can predict how much time. But I base criticality and develop action plans dependent upon how frequent the discharges are. The more frequent they become, the greater the criticality in getting it changed. But when you identify a tracking event, there should be an action plan put together immediately based on the analysis to deal with the equipment and address it on our terms, as opposed to allowing a failure to occur and have the equipment dictate the terms.
Okay, great. And I'm going to just ask one last question, and then any others that come in, like I said at the beginning, we'll do our best to get those answered offline. But just this one last one, asking about any particular books or presentations that give this kind of detailed guidance on how to interpret these sound files. So folks, maybe a couple resources you could throw out there for folks as they leave this webinar.
Well, the best advice I would have is for anybody interested in documentation should contact UE to get the proceedings manuals or CDs from previous Ultrasound World conferences. I have done personally a minimum of 6 or 7 presentations, and a large part of them deal with specifically analyzing files.
All right, great. I love that that free plug. So yeah, anybody that wants any of that information, certainly we've got a lot of it on our website, and also you can always email us, and we'll do our best to get those resources in your hands. So Joe, oh sorry, go ahead.
That's okay. The other thing I was just going to note is I will be at the upcoming Ultrasound World in May. So if there's anybody on the webinar that would like to have sidebar discussions, I'm happy to do that. I'll be at the conference for the entire time.
And that's a great segue, and I promise we didn't even ask Joe to say that, but that was great. So I'm just going to switch the screen back over to me. I've got just a couple more slides to show here to wrap things up. But Joe, that was a great presentation. This always is a hot topic, and as Joe mentioned, he has presented and done this kind of similar analyzing of the sound files at our Ultrasound World conferences. And just like we've been doing today, we do record these, and we will make this webinar available online. So for those that maybe want to go back and listen or share this with colleagues that couldn't make it, we did record this. We will put it online. And we do videotape the presentations from Ultrasound World. So these past presentations he's talking about, we've got those video recordings on our website. So when you have time at lunch or at the end of the day, definitely take a look at our website, and you can watch his presentations and learn a little bit more in addition to the other topics that were covered. So that was great. So up here you see we've got our website, uesystems.com. Just like I said, tons and tons of resources on there. We really do try to put as much information out there as possible because the more everybody knows, it's just the better for using our technologies and so on. So you'll see on there information not just on electrical inspection, but the other applications that ultrasound is used for. So we hope you'll take advantage of what we've got online. Get my screen here. We also want to make sure you know how you can stay connected and get connected with us. We do have our UltraProbe users group on LinkedIn. Just a great place for conversations to take place, questions to be asked. Joe's a member of that group, so he's on there, can possibly answer questions. those of you that are on the webinar today, if you've got questions that you want to post there, that's a great way to get a diverse group of responses to what you might be struggling with. And obviously we also hope you provide some advice and feedback as well. We're also on Twitter. You can follow us at UE_systems, and we have our sound advice blog as well. So just trying to find all different ways that we can be staying in touch with you, answering questions, getting you content and information. And lastly, we just want to make sure you've got the following dates. Our next webinar is going to be in January. The date is still to be determined, but we'll certainly get that out there to you as soon as we've got it. We're going to switch gears and move on to lubrication best practices, and Kim Hunt with Domtar is going to be presenting that webinar. She's running a just world-class lubrication program there and utilizing ultrasound as a part of that process, so we hope you'll be able to join us for that. Then in February, we're going to have Tim Goschert with Allied Reliability Group, and he's going to be talking about how to really dig in and select and build relationships with service providers so that you can get the best bang for your buck, and obviously really build those relationships so that you can take advantage of everything that they have to offer. And then, of course, Ultrasound World, our 9th annual, we're going to be down in Clearwater Beach, Florida with Joe, May 6th through 10. So definitely make plans to attend that. Get it on your calendar. You can even register, get your hotel rooms, take care of all of that before you sign off for 2012. And we've also got our full line of other training opportunities, our level 1 certification classes, steam trap examiner, so on and so forth up there as well for 2013. So take a look and start planning your new year. So again, we did record this. Once we've got it online, we will email all of you so you know when you can go back and view it. And I'll just leave this last screen on here as folks are signing off so you can see all of our contact information. But again, Joe, we just really want to thank you again for participating today, and everybody have a great rest of the day, rest of the year, and let us know how we can help. Thanks.
Thank you.